Okay, let's just start with this problem, problem 53, chapter 2. Here we have a projectile that we are shooting it from point A with initial velocity of u. So of course it's going to go up and gradually it's going to come down and hit the ground at another point. The distance from A to B in general is going to be a number, like for example r, which is given in this problem. It is 12 kilometers. And the question is, what is the minimum required velocity to shoot this particle to go up and hit point B? To explain this problem, it means you can at any if you shoot this particle at any given theta, you can always find the velocity to hit the B. For example, if you put theta is equal to 30 degree, if you shoot it with a small velocity, it's gonna go here, for example. If you shoot it with a very high velocity, it's gonna hit here, right? So if you change this u gradually, you can find the proper u to shoot to hit B, right? And the question here is, what is the optimum velocity, or what is the minimum velocity that we can shoot to hit point B? I'm gonna make this problem a little bit more general, then you can use that general solution to solve this particular problem with these given numbers. Let's say we have a particle that we are shooting it with a given velocity of u. And the question is, what should be this angle to have the maximum displacement for this particle? So again, let's say the velocity is given, the initial velocity. The initial velocity, let's say, is 100 meters per second. We can't change it. But you're allowed to change this theta to increase this displacement. What should be this theta to maximize this r? This problem is quite similar to Angry Birds, right? In Angry Birds, you have some velocity, but you can choose this angle to shoot that angry bird to hit the target, right? Let's say here our target is maximizing this r, and the velocity is given. We can't change it. We have some limited power to shoot this, right? But we are allowed to choose different theta. So the question is, what is the optimum theta? And after finding optimum theta, what's going to be r? What is going to be the maximum r? So I'm going to solve this problem instead of this particular problem. Okay, this is point A, this is point B. I would suggest to, before seeing the rest of the video, stop this, think about this problem at least for 10 minutes, then see the rest of the video. Okay, to solve this problem, I'm going to use the coordinates. And for simplicity, I'm going to put my coordinate here. So the origin of the coordinate is going to be at A. So initial x and initial y is going to be 0 because I put my coordinate here. So let's write it here. x0 and y0, both of them are 0. Initial velocity in the x direction is going to be u times cosine of theta. Initial velocity in the y direction is u times sine of theta. Okay. And this particle goes up and hits point B due to gravitational force. Now, what should I do here? Let's see what we have here, what piece of information we have in this problem that we can use it. First, we know initial point is x0, y0 is equal to 0, right? And also, we know the final point, which is point B. At this point, y is going to go to 0. And x is going to be my r, which I'm trying to maximize it. So probably the best option is starting by writing down the displacement equation for this projectile. So let's do that. Based on that equation, those two equations that I explained it in previous video, x is going to be equal to x0, which is 0, plus initial velocity in the x direction, which is u times cosine of theta, times t. And there is no acceleration in the x direction. We know that. And y is going to be equal to y0, which is 0, plus initial velocity in the y direction, which is u sine of theta, times t, plus 1/2 of acceleration in the y direction times t squared. So negative 1/2 of g times t squared. At point B, I know x is going to be equal to r and y is going to be equal to 0 because the coordinate of this point is 0 and r. And this point is going to satisfy the equations of these two equations, right? Because these two equations are showing this path. So we can do it, we can write it or rewrite this as this. At B, we are going to have x is equal to r is equal to u times cosine of theta times the time that it hits B. Let's call that TB. And same thing for the other one. Y at B is equal to 0 is going to be equal to u times sine of theta times TB, the time which it hits B, minus 1/2 of g times TB squared. And look at these two equations and see what is unknown here. If you look at these two equations, the only thing is unknown here is, let's say we know what is the velocity and also what is theta, right? I'm writing these two equations assuming I know what is initial velocity and also what is theta, the starting theta. So if we assume I have those two, TB is unknown. I don't know at what time it's going to hit the ground. So I need to find TB. We have a quadratic equation for TB here, right? So I can find TB using this equation. So if you look at this equation, TB is going to have two solutions. One of them is going to be 0. So TB should be equal to 0. Or it's going to be 2 times u sine of theta divided by g. So which one is the acceptable solution, acceptable time? Of course, this is going to be the time that we are looking for. 0 is the other point that y is going to be equal to 0, which is the starting point. So the physical meaning of the solution is the starting point, which y is equal to 0, because I'm finding this time from this equation, and this equation means when y goes to 0. The first solution belongs to this point, and the second solution belongs to the second time that y goes to 0. So this is going to be the time and our acceptable solution. So this is the time, and if I put it here, I'm going to be able to find r, the displacement. So let's do that. R is equal to u cosine of theta times this. So I'm going to have 2 times u squared sine of theta cosine of theta divided by g. So I found a relationship between the displacement, between r and the given velocity and theta. Now, let's go back to the original question. The question is, in what theta r is going to be maximum? There are different ways to find that optimum theta. One way, probably the easiest one, is this. From trigonometry, probably you remember, 2 times sine of theta times cosine of theta is equal to sine of 2 theta. So this is going to be equal to u squared divided by g times sine of 2 theta. So let me write that equation again. 2 times sine of theta cosine of theta is equal to sine of 2 theta. You should know this, which I'm using it here. Now look at this equation. R is equal to this, which is a constant number because u is a given number, g is a constant number, so we don't have any any flexibility here. Both of these numbers are given, but theta we are changing it, right? For any theta that we choose, sine of 2 theta is going to be a number between -1 to 1, and it's going to go to the maximum of it at 1, and it's going to happen when 2 theta is equal to 90 degrees. with theta is equal to 45 degree, right? So the maximum number for r is gonna be u squared divided by g, and it's gonna happen when sine of 2 theta is equal to 1, which means theta must be equal to 45 degree. So when we are shooting a projectile, we need to shoot it with 45 degree to have the maximum displacement, okay? And and r, the displacement of that projectile, is going to be u squared divided by g. You can use this general solution to solve this particular problem, problem 253.